Click the bell icon to get latest videos from Ekeeda.
Hello friends, in the previous lecture we have talked about that how can we represent the molecular orbital diagram for the oxygen atom, and similar to that we are going to talk about that is how can we represent the molecular orbital diagram for the fluorine atom. So let us understand this thing, and with the help of the previous one we will help out to how can we draw the molecular orbital diagram for fluorine. So before understanding that how can we represent the molecular orbital diagram, what we should understand that how can we represent the atomic orbital diagram for the fluorine atoms, and then only we would be able to do the molecular orbital diagram. But before moving to that one, we should know that how can we represent the electronic configuration for that of the fluorine atom. So let us understand that how can we write the electronic configuration of fluorine atom. So fluorine, which has an atomic number of 9, can be have the electronic configuration that can be represented in this way, that is 1s2, 2s2 and 2p5. So in the previous lecture we have also got to know about in the valence bond theory also, as well as in that is hybridization. So in this case basically the bonding it helps because of the presence of the unpaired electrons that are present at the outermost shell, and that's the reason that the outermost shell is nothing but the 2s along with that of the 2p. So therefore this will be the main reason that the fluorine will form a bond with that of the other fluorine or with that of the other atom. But in this case, because we are learning about the fluorine molecules, that is we are going to talk about that is F2 molecule. So obviously in this case basically one fluorine atom will be bonding with that of the other fluorine atom, and that is how the whole sequence is. So now we are concerned with that of the outermost shell, or we could say that the outermost orbit, and that is the reason that the outermost shell consists of basically the two subshells, that is S subshell and P subshell. And talking about the S subshell, it consists of basically one orbital, while talking about P subshell, it consists of basically 3 orbital, namely as Px, Py and Pz. So now let us fulfill the electrons that are being present in the outermost shell, and that is basically because in S subshell there are 2 electrons, so therefore I am filling it 2 electrons. While talking about the P subshell, that consists of 5 electrons, and the 5 electrons in that are being present in the P subshell can be fulfilled in the terms of that is Hund's multiplicity principle, and that is how it is being fulfilled, like 1, 2, 3, 4 and 5. So this is what I have mentioned about this one. So therefore let me represent that is this one is Px, this one is Py, and this one is Pz, while this one is 2s orbital. So just as a reference that it would be very much helpful in making the atomic orbital diagrams or making the molecular orbital diagram of that of the fluorine molecule. So this is what we have, but in fluorine molecule, that is 2 fluorines are being involved, so as to they will form bonding with it. So therefore we have to separately make the atomic orbitals in terms of their energy level, and let us draw that. So this represents the energy level for their respective, that is the orbitals. And talking about the first orbital that we have, that is if we refer this electronic configuration, then for fluorine, that is the first orbital that we could see is that is 1s orbital. That is what I could represent over here. That will have a particular energy level. Similar to that of the another one, that is 2s orbital, obviously that will have higher energy level, because according to the Ampere's principle, obviously 2s orbital will have higher energy level, and that is how I can represent over here. And talking about the next one, that is the 2p orbital, obviously it will have higher energy level, higher energy compared to that of the 2s orbital. So that is what I am representing over here. So this section is basically what I am representing is I am representing the atomic orbital for fluorine atom. So similarly, I could also represent the atomic orbital with respect to their energy level. I can also represent the atomic orbital for the another fluorine atom that is responsible for us to forming a bond with that of the another fluorine atom. Obviously, the energy level would be the same. So similarly, here the energy level would be the same for that is for 1s, that is for 2s, and this is for that is 2p. So this is a rough diagram that I have mentioned over here, just as to indicate that these are the energy levels. So now let us fulfill the atomic orbitals for that of the fluorine atom. So in this case I would see that there is presence of one orbital in the 1s. So this is for 1s I am talking about. So this is for 2s, and this is for 2p. So this is what I have indicated. So similarly I could mention it over here also. That is for 1s, for 2s and this is for 2p. So now let us fulfill the electrons, and similarly we can also take the reference of this one, that is by looking at this we can fulfill the electrons. So this 1s consists of 2 electrons, while talking about the 2s it also consists of 2 electrons, and talking about the 2p orbitals, so this is what I am representing about 2p orbitals, in which basically 1, 2, 3, 4 electrons are been there. Here also 1, 2, 3, 4 electrons are been there, and here basically similarly it is the same. So now what we have to do is we have to combine these two atomic orbitals of the fluorine atoms, and because of that only the molecular orbital will be formed. So talking about the last one, that is the energy level that we have, that is the 1s orbital. So the 1s orbital, because it is very much near to that of the nucleus of the fluorine, and that's the reason that it won't take part in the bonding. And we have discussed this about in our earlier lectures also, that is according to the valence bond theory also, we could say that the outermost shell is responsible for giving the bonding, or that's the reason that and which consists of basically unpaired electrons. So this doesn't consist of any unpaired electrons, so therefore it won't form any kind of bonding. So therefore this is what I would say, that this energy level or this atomic orbitals are basically known as non-bonding orbitals. Obviously because of the presence because of the absence of the unpaired electrons, and because it is very much near to that of the nucleus. And talking about this 2s orbital, so this 2s orbital can be responsible for giving the bond, but still it won't take part in the bonding, but still it can be whenever these two atomic orbitals they will come close to each other. Obviously there would be a difference between those energy level, and that is what we could see. And the energy level is now being separated into two parts, that is the one energy level or the one atomic orbitals, one of the two YF, that is the molecular orbital, will have now two energy level, and this is the lower energy level while this is the higher energy level. So again it consists of basically two orbitals, so one orbital will be down while the one of the orbital will be in the upper energy level, because obviously we have got to know that it is a molecular orbital, it is the combination of the two atomic orbitals with having the total number of atomic orbitals, and that is what we have got. So in this case basically we have involved two atomic orbitals, and that's the reason we are getting two molecular orbitals, and that is one is of lower energy level and one is of higher energy level. So now this is a thing from which we could compare this. So let me compare this one. So this is just a comparison that the energy level is basically divided into two parts if we talk about this one. So this is what we have an energy level, and this is also we have a molecular orbital that has a particular energy level. So now by fulfilling the electrons, so there are a total number of 4 electrons that are being present in this energy level. So therefore we can that is fulfill the electrons in this molecular orbitals according to the Ampere's principle and according to the Hund's multiplicity rule. So therefore we can fulfill it by 1, 2, 3 and 4 electrons. So this is what we have represented over here. But every orbital or every molecular orbital has a particular designation, and we denote it with a particular value, or we denote it with a particular name, and that is the reason that the name of this one or the designation of this molecular orbital will be basically sigma 2s orbital, molecular orbital, while this one would be basically sigma star 2s orbital. So this is what I have represented for the 2s orbitals. And now let us move on to the next one, that is 2p orbital. So now talking about that is this 2p subshell, and this 2p subshell actually it consists of basically 3 orbitals, as you could see. That is one is I would write it over here as 2x, 2px basically. Now this is 2py and this is 2pz. So similarly I could also write it here as 2px, 2py and 2pz orbital. So this is what we have represented over here, and now the next of the thing is what we have to do is we have to basically fulfill the electrons, and that is what we are going to do. So here basically there would be basically 5 electrons, so I am representing it over here as in this way. So now when this of the two orbitals, when they will come close to each other, obviously they will form a molecule, and that's the reason that the energy level can be distributed or can be written as in this way, where I could see that the lowermost energy level, that would be because of this 2pz orbitals, because they are responsible for formation of a sigma bond, and that is the reason that one of the sigma 2pz orbital will be down, while the one of the opposite one, that is the sigma star 2pz orbital, that will be at the higher energy level, and that is basically the anti-bonding orbital. And the rest of the thing is basically we'll get another energy level, that is which will consist of two orbitals, and even here also in opposite way we can get this as two orbital. So talking about the next thing, that is this is the one that will consist of an orbital, while this it will have basically two orbitals. Here will be two orbital and here will be basically one orbital. So now what we have to do is we have to just because just as to showcase that there is difference in the energy level, so I'm mentioning here with the dash one, just as to represent that there is difference in the energy level. So this is what we have to do. So these are the energy levels. So that's the reason that whenever these two atomic orbitals they will come close to each other so as to form bond, obviously they will make them disintegrate in such a way that they will have different kind of energy level, and that is what we are observing over here. And let us designate those molecular orbitals. So these are the molecular orbitals that we have, and let us designate that. So this one is the responsible for giving us, that is sigma, that is 2pz orbital. This is, while this is basically, this is the responsible for giving the pi bond. So therefore this is known as pi 2px, while this one will be pi 2py orbital, while this one will be basically pi, because it will be opposite to that one. So therefore this will be pi star 2px orbital, while this one will be basically pi star 2py orbital, while ultimately that is the last one that will have basically known as sigma star, that is 2pz orbital. So this is what we have. So talking about the next other thing, and what we have is in this energy level, that is in the 2p orbitals of both the fluorines, the total number of orbitals that we have is basically 6 orbitals that we have, and total number of electrons that we have is, as you could see over here, that is 5 electrons are present over here as well as 5 electrons that are present over here. So making a total of basically 10 electrons, and those 10 electrons, what we have to do is we have to fulfill in the molecular orbitals. So this is what we have. So this all section that we have is basically known as molecular orbital for basically fluorine molecule, that is for F2. And while fulfilling the electrons, obviously we have to consider the emboss principle as well as we have to consider the Hund's multiplicity rule, and that is what we are considering in this way. So therefore, if we know that there are basically the presence of basically 10 electrons, so that could be filled in this way. So I'm filling it with 1, 2 electrons are being filled. So left is basically 8 electrons, and then next is third. The fourth one would not be filled over here because we are following the Hund's rule also, and that's the reason this would be the fourth electron. Again, fifth, sixth, then seventh, eighth, ninth, and 10th. So this is how we have fulfilled the electrons in the molecular orbital of fluorine molecule. So this is what we have, and basically we are seeing that we are concerned with that is of molecular orbital for the F2 molecule, and that's the reason that we can see multiple energy levels, and which is completely different with that of the atomic orbitals of the fluorine atom only. So this is what we have. So if you have got this, so it is very much easy for us to understand that how can we represent the electronic configuration for the fluorine molecule, and that is what we are going to represent over here. That is the electronic configuration for fluorine molecule can be represented as you could see over here, that is this is a non-bonding orbital, but this non-bonding orbital is made up of, that is 1s orbital and again 1s orbital, and that's the reason that two kind of orbitals would be created over here, but that's the reason that we know that it doesn't play any vital role in forming a bond. So still we can represent it over here in this way, that is sigma 1s, and that consists of basically 2 electrons, and again there will be basically sigma star 1s, that will consist of basically 2 electrons, and following that what we have is sigma 2s. So this is sigma 2s, which consists of 2 electrons, and again there will be another one, that is sigma star 2s, that will consist of 2 electrons. So this is what I am representing over here, and the rest of this is what we have to represent. So the next of the energy level that we have, or next of the electronic configuration that we would represent, is basically sigma 2pz. So this is Z1, and that consists of 2 electrons, and later on what I could see is that is pi 2px, that consists of 2 electrons, and again pi, that is 2py, that consists of 2 electrons. So this is how I'm arranging it according to the energy level or according to the emboss principle. So that is how we represent the electronic configuration also. So similarly we are applying that theory only. So after that what we could observe is basically pi star 2px, and that also consists of 2 electrons, and the next is basically pi star 2py, again that consists of basically 2 electrons. So this is what we have electronic configuration we have represented for, that is of fluorine molecule. So now let us represent the what is the bond order, and what for which we know. So as I have discussed earlier also, that is the NB represent the number of electrons that are present in the molecular orbital, bonding molecular orbital. While talking about the Na, that is the number of electrons that has been present in the anti-bonding orbital. So if you observe the last one, so because the last orbit or the last structure is basically the main responsible for forming a bond. So therefore, in this case, because we could see that the bonding orbital, it consists of basically 6 electrons, while the anti-bonding orbital, that consists of basically 4 electrons. So I would write over here as 6 minus 4 divided by 2. So this will give me 2 divided by 2, and that is nothing but 1. So therefore the bond order for the fluorine atom or fluorine molecule, that is what I'm talking about, that is 1. So it clearly indicates that the bond between the fluorine and that of the other fluorine, so because they are forming a bond, and that the number of bond is basically 1, and that is the reason that we represent fluorine molecule in this way, having 1 bond. So this is what the molecular diagram of the fluorine molecule is, and not only it gives the electronic configuration that we have got over here, but it also gives a very deep detail about what is the energy level for that is of the atomic orbital also, as well as for the molecular orbital also, and electronic configuration along with that of the bond order that we have got to know now. So there are various details that we could get because of this molecular orbital theory, and this is what we have. So thank you friends for watching this video. I hope you have understood this video very clearly, and you have got to know that how can we represent the molecular orbital for that of the fluorine, and make sure that you should not miss any kind of electrons while writing the molecular orbital. So thank you friends for watching this video. I hope you have understood this video very clearly, and you share this video with your friends, and yes, don't forget to subscribe Ekeeda channel. Thank you so much.